Hello, good evening. Okay, this video we are going to go through the St. Patrick prelim paper that I gave to my Bravo group. So I just want to make clear that this prelim paper is actually made in the 2016, and during that time, the trend is that school will set an extremely hard prelim paper to so-called wake the student up and then try to motivate them to actually work harder. So the underlying mindset is that if they get too good a mark for prelim, they will get complacent. So that is what happened in 2016. Ever since we studies in the educational field actually shown that it actually doesn't motivate the student. So now the trend is that, like for example in this year or last year, our school actually set the prelim paper at a difficulty that is very similar to O-level. So that's why I'm now using this 2016 paper to actually try to expose you to higher level question, and then in doing so we will try to fish out the content gap that you have. It's either you have a content gap or you couldn't apply it to context. Okay, so the question that you surface is actually some interesting question. So in this video I will be going through this 1 2 3 4 5 6 7 8. We are going to go through these 8 questions. So this video most likely will last like maybe 45 minutes. So if you do not have the time, what you can do is that you can skip forward. I will try to put the timestamp for each question in the description below. So let's start. The first question will be question 8. So let's take a look at question 8. So question 8 is a question that you need to that will test you on your free body diagram. Then after that you need to apply moments to it. So it is actually kind of challenging because there are actually 2 pivots. So let's try to do this. So here we know the mass, that means we can find the weight, and then you can see that it is a vertical ice wall, meaning that there is no friction. So here it says negligible friction. So in another word, basically the friction on the ice is actually 0. Okay, then after that we are told that the L is actually equals to 2.1 meter, and we have a CG that is 1.1 from the feet. So basically this D is 1.1, and we have to find out the frictional force between the feet and the ground at the verge of slipping. So at the verge of slipping, basically you can interpret it as it is just at the critical point whereby the sum of clockwise moment is equal to the sum of the anti-clockwise moment. So at the verge of slipping, meaning that any change to the forces or the distance would result in one of the moment, clockwise or anti-clockwise, being larger, and then that will result in a net moment, and then the whole thing will just rotate. So you need to visualize that if this guy is to slip, it will slip this way, right? The head is here, and then after the body, then the leg, right? So it will slip this way. So why is it that we need to visualize this? Because we need to find out which direction is the friction acting. So since the hand over here has no friction because friction on ice is 0, so we don't need to visualize that. We just need to focus on this part here, the feet and the ground, between the feet and the ground. So as you can see, the feet upon slipping will actually move to the back. So this means that the frictional force at here will act to the front. Okay, so we need to know the direction of forces first, because later on we are going to decide whether this force is going to be clockwise or anti-clockwise. Other than that, we also have the weight, yeah, and of course whenever you have contact, you would have normal contact force. So these 2 normal contact force will be different from each other, so I will call it N2, and then I will call it N1. So upon saying this, we also realize that there could be 2 possible places where we can tick as the pivot. Now the trick about selecting pivot is that you want to select a pivot so that you eliminate one of the unknown that is not your objective. Objective being what the question is asking for. So in this case, the question is asking for the friction between feet and ground, right? So meaning that you want this, the one that I highlighted. So we want the frictional force between the feet and the ground. So if we want that, we cannot use this as the pivot, because once we use this as the pivot, when we write the moment equation out, I would have to use friction multiplied by a perpendicular distance. So if I put the pivot like here at the feet, then there will be no perpendicular distance and my friction will be just disappear from my equation. So I couldn't do that. So a smart way of doing this is to actually put the pivot like on the ice down here. So by putting it there, that means the moment caused by my N2, I do not need to write in my equation because there's no perpendicular distance between the pivot and the line of action of N2. So in that way, I will put the P there. So that is one trick. So in this question, you also learn like selection of pivot. Okay, so you will always put the pivot at a place whereby it will delete one of the useless unknown that you are trying to find. So of course, step one is to actually draw the free body diagram, which we did, right? So we did this, we did this. So now we need to simplify the thing, and then we need to go and figure out which is the perpendicular distance and all that. So down here, what I would do is that I would simplify it for you. So now I have this object which is like that, and then the ground is here, and then I have the ice wall over here. Okay, so this blue line represents the body. So instead of looking at it as a body, we can think of it in terms of a stick, which is easier. Then we know that now my pivot is here, right? And then we have three forces to consider. W, right? So if I look at W, what is my perpendicular distance? I would have to first draw my line of action. Then I know that, oh, okay, this is my perpendicular distance, right? So this is maybe dw, right? So to find dw, how can I find dw? Now this is tricky because that means I need to find this, right? I need to find this, correct or not? So now that I know, then I will look at this in a different light. So I have 2.1 over here, and then I have 1.0. So I get the 1.0 from here. Yeah, then I have this, right? Then I know that down here, from here to here, would be 1.1, right? From here to here. So that means this over here, the red one, will be 2.1 minus 1.1, which is 1.0, right? Down here would be 1.0. Yeah. So how do I find this this one that I need to find? Oh, what a tricky thing. I need to find this, right? I need to find this. Headache. Any easy way to find this? Looks like I need to use trigonometry, right? So I need to find the angle over here. So if I call this angle theta, I would know that I can use cosine rule. So I have cosine theta equals to what is that? Adjacent over hypotenuse, right? I would have adjacent over hypotenuse. So if I do that, I can make use of my calculator, right? And then I would have arc cosine bracket 1 divided by 2.1. I would get around 61.563, right? So if I do the same, I would have this as my theta. So with that, I can actually find my d1. My d1 would be cosine theta d1 over my hypotenuse, which is 1. So I am using this. In case you didn't follow, cosine theta will be equals to d1 over my hypotenuse, 1.0. So if I do the thing right, I would have d1 equals to 1 times cosine theta. 1 times cosine theta would be 0.4762. Sorry, I shouldn't call this D1, this is DW, the distance for W. So I have that, so I'm happy with it. Now I need the perpendicular distance for the friction. So let's look at the first diagram. So let's look at this diagram. This is the line of action of friction. So if this is the line of action from friction, that means this will be my perpendicular distance for distance over friction. So distance over friction, quite easy, right? I can use Pythagoras theorem, right? So if I look at this, then if I want to find this in the second diagram, if this is DF, it will be perpendicular, it will be the right angle triangle, right? So this hypotenuse is 2.1 and my base is 1, right? So I can actually find my DF. So DF would be equals to square root of 2.1 square plus 1 square. So that would give me 2.1 square plus 1 square. That would give me about 2.326, right? I will just leave it there. And then after that, I need to find the perpendicular distance about N1. So N1 is over here. Look at the first diagram. Line of action of N1. This is my pivot. So therefore, this would be my distance for N1, right? So distance for N1 is quite straightforward. It will be simply 1.0. So now I have all this D1, DF and all that. I can then write my equation. So I will take moment about P. So I should have my clockwise here and then I should have my anti-clockwise here. So what are the things that will give me clockwise? What are the things give me anti-clockwise? So I don't need to consider N2 because there's no what. I'm looking at this diagram, okay? So I can see that the weight over here is giving me a clockwise moment, right? So I will take W times dW, okay? Then I can see that my friction over here is also giving me a clockwise moment, right, about P. So therefore I would plus friction times the distance for friction. And if now I look at N1, I can see that N1 will be producing an anti-clockwise moment. So I would have N1 times dN1, right? So now I substitute the numbers in it. So W is from here, 80 kg, so it will be 800. dW I have found, which is here. So dW is 0.4762. Friction is what I want to find. And distance for friction is 2.326. N1 is an unknown. dN1 is 1. So now I got a problem because I have two unknown. So what I do, I use my second condition for anything in equilibrium, right? So second condition for anything in equilibrium is that F net must be 0 in both the vertical dimension and also the horizontal dimension. So now I want to actually attack the N1. So if I look at this, N1 is upward force and is in the vertical dimension. So I'm looking at this. N1 is in the vertical dimension. So that means I want to actually equate all the vertical. I want to equate all the vertical F net to 0. So my vertical F net consists of N1 and W. So W, I know W is 800. Oh, by the way, they are in different directions, so it should be minus. And N1 would be here. So now I know that N1 is 800. So with this, I will substitute. I will go back to my main equation. I will have 800, 0.4762 plus F 2.326, and then n1 would be 800 times 1. So when I solve this, I will get an answer for F. So that's question 8. And like I said, it is ridiculous to actually set paper 1 question with such complex mathematics. You need to find the D with trigonometry and all that. So it is not easy. So in this question, main thing you need to know, first you need to learn how to draw your free body diagram. After that, you need to learn how to select P and select a pivot. So this one is a pivot, okay? Then after that, you need to be able to decide, okay, which force will give rise to MCW or then MACW. And then you also need to make use of two things. At equilibrium, you need to make sure that F net is 0, and of course you will have your M net, which is 0. So M net equals to 0 is another way of actually saying this lah. Okay, Ken? So this F net equals to 0, be careful. You need to look at both the vertical dimension and then you look at the horizontal dimension, and do not mix all the forces up. You can do it like vertical first and then you can do horizontal first, but I don't think O level will torture you like that. Maybe in paper 2 in rare cases, but I don't think paper 1 will make you do such a elaborated calculation for just 1 mark. Okay, so let's move on to the next. 13 actually is testing you on KMM, kinetic model of matter. Essentially they are actually testing you on the P, V and T relationship. So down here, you need to know a few things. First, you need to know how P is related to V, which is actually an inverse relationship. And then after that, you have two more relationship, which is direct. So you need to know these two. Now, after you know this, then you need to be able to write the linear equation for these three relationship. So if your math is not that strong, you will face difficulty. So for this, you will get this linear equation, and then for this you will get this linear equation, and then for this you will get this linear equation. So for this particular question, we will be focusing on this, and once you know this, then you can write this PV equals to K. Now what does this PV equals to K means? It means that if you have a table of these three parameters, and if you do an experiment whereby you take V as the independent, and then after that you measure the changes in the pressure. So for example, you could start off with a volume of 100, and then after that you measure, oh okay, my pressure is 10. So once you have this, you will be able to find PV, right? PV will be equals to this, and then after that you change your volume will be to 200. And of course, if you pull this piston out to 200, you will get a much bigger volume in here, and then your collision frequency will definitely drop because of number of particle per unit volume will actually drop. So because of that, the pressure will also drop, and you will realize that because of this law, the drop in your P will be such that your PV will get back the same volume. So if you continue to do that, you would realize that, oh, if I increase to 1000, I will get 1. So no matter what you do, you will find that this PV value will be equals to a constant, which is K. So now if you look at this, then what does it mean? Imagine if you do a graph like A. No matter what V value you get, for example 100, 200, and in the end 1000, right? Doing this, yeah, can you see my red color pen? You will get back the PV value of 1000. So meaning that you will get 1000 here, you will get 1000 here, and then you will get 1000 here. That's why eventually you will get back a straight line. So this requires some mathematical knowledge. Okay, now how about C? If you look at C, can we do a mathematics and find out? So we know that what governs them is this, right? If we do this, then we will get P actually equals to K times 1 over V. If we have this, then what it means, can you see that it is actually equals to Y equals to mx plus C? Yeah, because now your 1 over v is your x-axis and that your p is your y-axis, right? So you should be getting so if you look at the governing equation, which is this, it is plus 0. So c is 0, which is correct, and you will have a constant gradient, which is this. So you know that your c is also correct. Now we will analyze the b and d. So b and d is about p and v. So if you look at my table over here, do you notice that when v is becoming very big, p will actually become very small? So I would say something like, if I were to plot p and v, when my v is becoming a very large number, I would have a p that would have been like a very small number. And if I have a v that is very small, in order to get back my PV equals to a certain constant, my p has to be like really large. So because of that, I would expect myself to have this point and this point, right? And you will notice that as my v become extremely small, my p will become extremely high. This means that I would have an asymptote over here. So this thing will just keep on going to infinity. This one will be just keep going to infinity. And so I know that D is also correct. Okay, now question 14. Question 14 is a test on your pressure equation. So for your pressure equation, what you need to know is that at the same liquid level, the pressure acting on that level should be the same. So if we look at this, basically the before diagram has very little information for us. We only know that when there's atmospheric pressure pressing onto all 4 levels, they would be at the same level. So there's not much info to be derived here. But in your second diagram, there's quite an interesting turn of event. What happened is that you notice that on here, the level actually go up. This means that the trapped air over here has actually less atmospheric pressure than the outside tube, than the left hand side tube. So what you can do is that you can actually set up 2 equations and you will have 2 unknown. You will need to solve it simultaneously. So let's try for me to illustrate for you. So let's say I look at the left hand side first. That means I focus on liquid P. I would set this as my reference level. Then I would compare these 2 points. Let's call this 1 and 2. Okay, and I can see that at 1, the only pressure acting on 1 would be from the atmosphere, right? And then if I look at 2, then the pressure will be from this liquid column plus whatever gas that I have inside. So if I were to write expression relating P1 and P2, I will start off like that, right? Because they are, I set it as I'm analyzing the same level. So for P1, I would have my atmospheric pressure pressing on it. P2, like I said, there will be a pressure from the column plus whatever gas that is inside my sealed chamber over here. Okay, so after they close the tap, actually the pressure is reduced. Somehow they suck out the air. So now if I want to write out an expression, I do not know what is my P atmosphere. So I cannot assume and put a number there. So I'm just going to put this. The pressure from the column has to come from the liquid. So I know that the expression for this, when I expand it, will be rho GH plus P gas. So for this is liquid P. Liquid P, I already know my density, which is given here. So I will just put down here, right? And I notice that this guy is in cm cube, so meaning that I don't need to convert my h. Do I need but my g is in meter per second square. Interesting. I think for simplicity's sake, let's convert it. I'm not sure whether the g will get cancelled or not. So I think let's convert it. So as you can see, their requirement for this paper is really high. You do so much conversion. How to convert this? Can I don't convert this? Okay. I decided I won't convert this, but I will just remember that my g may not be 10. Okay, because 0.80 is in cm cube, and then after that my h over here is also in cm. So I better leave my g as g. Okay, then I plus P gas. So I have this. Let's just simplify it. Normally I will do it at the last step, but you guys told me before that you don't like to see such big chunk of things. So I do this plus P gas. Right? So I have this expression, okay, and basically that's it. That's all I can do. What I need to do now is that I want to do similar thing for liquid P, and I just want to see if I can take another equation and then solve this thing. So what I want you to do now is to pause the video. Maybe you can actually write the equation for P3 equals to P4. Okay, so P3 is quite similar, right? You will have, you know, and then P4 you will have, you know, yeah, and then, you know, yeah. So I want you to pause the video and then try it yourself, okay? Then after you are done, you can unpause the video and see whether you're right or not, okay? So I hope you have tried, and while you're trying, I realized I also made a mistake, so I make some changes over here. So be very careful. I think I blocked my own, I didn't notice it because of my sketching. So if I erase all this, you can actually see that this 15 is measured from the bottom, but what I want to find is actually the liquid pressure caused by this bit, which is 15 minus 5, so this is 10. So that's why I make a change over here and I get this. Now if you do similar things, you will actually get back this expression, and the height of course is 12, so it's 16 minus 4. Yeah, so after you do this, you realize that you can actually equate the two equations, and basically you can just take this entire equation minus this entire equation, and you will get, and basically you eliminate P atmosphere and P gas. So if you do your math correctly, you take equation 1 minus equation 2, okay, you will actually get something like this. So for me, I do this way, Hg plus P gas minus this entire thing, right? 12 rho G plus P gas. Right, so basically if I do that, then PG I get 0, and then this I will get a chunk of number which is 8 G minus 12 rho G, oh, no space, minus 12 rho G, then this is plus 0, then P atmosphere I get this. So if I do this, I will get 8G equals to 12 rho G. So basically I can delete the G, yay, I don't need to care whether it will affect my unit or not. So after this I get this, so I get my rho equals to 8 over 12, and then this rho will be the density of Q, which is this 0.67. Do I get the answer? Yep. Okay. Okay, for question 20, there is actually a mistake in the answer key. So I have selected the wrong answer, but I have given you the correct explanation. So if you notice that you couldn't understand this, good for you. That means you have read and then you are very critical. You realize that something is off. So I'm very sorry about this. So let me go through this very quickly. So number one, very easy. You should start your heating graph at minus 10. So I have this, I have this, I have this, I have this. So I cannot eliminate anything. But I know that the ice is going to melt at 0. So I would expect constant temperature at 0, because during melting the temperature won't change. So I know that this 2 is correct, and I can basically throw this off. Right? The other thing that I noticed that I can quickly eliminate before I need to do any thinking is that for ice, it has a lower specific capacity than water. So it means that for ice, I need to, for water, I need to absorb more energy before my temperature can rise. So I would expect the curve over here to have different slope. So because of that, A will be eliminated, because I would expect the gradient of ice and water to be different. Okay, so I know that this is gone. So let me clarify, how do I decide whether it's B or whether it is C? Okay, so for this, you need to understand specific heat capacity. So basically, if I have a high specific heat capacity, what it means is that I will need lots of energy before my temperature can rise to bring it up to 1 degree C. So if now I analyze just B and C in the water part. So let's say I took up maybe this amount of time. So since the heating is done by the same heater, within the same amount of time, I should supply the same amount of heat to my water. So if I look at this time interval, I would be able to see that, oh, the temperature rise would be from here to here. This is my temperature rise, right? This is my energy supply. Okay. Now if you look at what I have drawn, basically what you need to understand is that if it absorbs this amount of energy, my water raise this amount of temperature. So if we look at the ice in the same thing, if now I supply so down here, can you see I supply a much smaller energy, and for the ice I can already produce such a big temperature change. So actually, if I'm looking at B, I can actually already see that my water actually has a higher heat capacity than my ice, and that agrees with the statement given in the picture's context. So I know that B is correct. Now, just to confirm that your understanding is correct, can you check whether C is correct or not? So for C, I need to supply this amount of energy before the temperature can rise, compared to this amount of energy for this temperature rise, which is bigger. Okay, so now you analyze and you can see that C is wrong, right? For question 21, it is still testing on your understanding of specific heat capacity. So now what happened here is that they are commenting how ice actually cools a drink. So what happened is that if you use ice to cool drinks, you would expect the ice to absorb the heat from the drink and thereby cooling it down. So for ice, when it absorbs heat, it will undergo two things. It will first melt, and then after that, it becomes water, and then it will absorb even more heat until it reaches thermal equilibrium with the rest of the drink. So down here, if you look at the four options A, B, C, and D, if you have a low specific heat capacity, or that you have a low specific heat latent heat of fusion, what it means is that it just need to absorb a very little bit of energy from the drink, and then it will either melt or it will either change temperature. And if that is true, then you can't really cool your drink properly, right? Because you want the ice to absorb lots of energy from the drink before there's a temperature change or before it even change state. So because of this low, and what it means over here, it absorbs very little energy from the drink, it means that these two options are out. Then we look at C and D. For C and D, you realize something very strange, and that is latent heat of vaporization. If you have latent heat of vaporization, that means you are waiting for the ice to turn into gas. And in order to do that, you need to reach at least to a temperature close to 100 degrees C. And if your drink is like just 40 degrees C and you add ice in, the temperature is just going to go down. It will never go up to boiling point. So you know that D is definitely out. So let's look at C. C talk about latent heat of fusion. Latent heat of fusion is the amount of energy that is responsible for melting. And if you have a very high specific heat latent heat of fusion, that means that the substance will take in lots of energy before it will actually change state. So if that is true, and if that is ice, that means you can actually take away a lot of energy before the ice has completely melted. And that is your purpose, right? You want to take away energy from the drink so that the temperature of the drink will go down. So therefore C is the correct option. For question 22 is actually a very simple question, but they are trying to intimidate you by introducing this thing called rate of water flow. And you will see that this weird thing come out, joules per minute. So if you are not really comfortable with playing around with units, you can actually write a statement in your working and say that I'm going to analyze the heat exchange, sorry about the spelling, heat exchange in 1 minute. Meaning that if you are doing this analysis in 1 minute, what is the amount of heat removal by water? It will be just 6.7 times 10 to the power of 9 joules. You can just ignore the per minute because you are analyzing it for 1 minute. Okay, so you can then simplify the whole thing, and then you will have this peace of mind. If you do not want that, what you can do is you can also take a look at the option is always per second. That means they actually want you to analyze it in 1 second. And what you can do is that if you look at this same thing, this 6.7 thing is for 1 minute, right? And you know that 1 minute has 60 seconds. So basically you can quickly change this rate to something that is useful to you. So you can actually do 6.7 times 10 to the power of 9 divided by 60 seconds, and you will get the rate of heat removal by the water in seconds. So if you do that, let me try. Oops, sorry, I pressed the wrong thing. 6.7 divided by 60, you will get 0.11167 times 10 to the power of 9 joules per second. So in 1 second, that is the amount of heat removed by the water. Okay, so basically you are using water to take away heat from the nuclear power station, and when you remove the heat by water, the water will actually rise by how many degree? 14 minus 6 will remove the water. When it get ejected, it will be 8 degrees Celsius higher than it enters. So basically you want to know how much water you need to supply in 1 second in order to remove this amount of energy per second. So quite straightforward. You know the equation for heat loss. Q is equals to mass times specific heat capacity multiplied by the temperature change, right? But now you want to analyze energy removed per second. So what you can do is you can divide by per second on the left hand side, and by mathematics you also know that I have to do this. So if I do this, that means I can choose where this per second goes. It can go to m, c, or delta t. And of course, since you want to know rate of water flow, most likely you would want to bring it over here. So your equation will be changed to this. Yeah, this is if you have a very good command in your algebra. If you don't have, what you can do is like what I tell you at the beginning. You can begin the analysis. You can analyze it in a step of 1 second. So you can do this, right? And from the rate that is given to you, you have already found out that, oh, every 1 second I need to remove this amount. So then your Q will become this amount, right? 0.1167 times 10 to the power of 9 equals to mc delta theta. So if you find out the mass, this is the mass you need to remove in 1 second. So in a way, you actually solve the question as well. So let's see whether there's difference. So down here, Q over S, I'm looking at the left hand equation. I'm looking at this one, okay? I actually already find out, right? So it will still be 0.11167 times 10 to the power of 9 equals to the amount of mass I need to remove per second multiplied by specific capacity, and I would raise the water by 14 minus 6, which is 8. And basically if I solve meter per second, I would have this times 8, then I would have this 0.1167. So this is actually since the format is like that, divide by 60. So divide by 60, if I do the math correctly, divide will become on top, so I will get this. Yeah, this is to the power of 9. If I do the same thing over here, I will get back the same thing, right? I will get 4200 times 8, and then I bring this over to here. So then I would have a 6.7 times 10 to the power of 9 divided by 60. Can you see that I will get back the same thing? Yeah, but this will be the mass to be removed in 1 second. Yeah, so I will get back the same thing, and if you look at this, then I think the answer would be B. Yeah, so that is for your question 33. Don't worry, I don't think O level will give you this, because you really need to have a firm belief in what voltage is. So what is voltage? Voltage basically tells you how much energy is being carried by 1 coulomb, right? Sorry, coulomb is C, right? 1 coulomb. So when the charge come out to this point, it is still carrying 6 joules per 1 coulomb. From here to here, there's no component for the charges to release the energy, so even up to this point, it is still 6 volt. By the same logic, when the charge come over here, go down all the way till S, there's no energy loss from the charge ideally, so I would have 6 volt. So far so good. Now what happened is that when the charge come back to the battery, it has to carry 0V. Somehow the charges know how much energy to give away, and when it return, it will just be 0 volt. So by the same logic, now we do reverse engineering. From here to here, there is nothing for the charge to give energy away. So it means that when the charge come over here, it would already carry 0 joules per coulomb. And by the same logic, if I look at this, I can see that the charge over here is also carrying no voltage. Now once I have this concept map, then it is quite easy, right? Potential difference between R and S. What is R? R, I have 0 volt. S, I have 6 volt. So what is the potential difference? 6 volt. So that's how it goes. Okay, but this is JC stuff. Yeah, you can apply this concept in your secondary syllabus also. Sometimes it will help you simplify. When you want to find potential difference, this will actually help you find the potential difference. Okay, for question 37, I would rather you come and see me if you have problem, because you required you know, like the application of right hand grip rule and things like that. But I will try to help you visualize. So basically they gave you 3 types of magnetic fields, and they want you to actually answer what produces them. So down here, if you look at the first one, which is this, you can see circular fields and all that. It means that it has to be a straight wire. So a straight wire has 2 options. Either you have a current going out, or going out of the page, so it will be like that, or it can be a current that is going into the page like this. So if you apply your right hand grip rule correctly, when you have a current that's like that, you will have circular fields, and that would go this way. And if you have a current that goes like that, you would have a circular field that goes this way. So if you apply your right hand grip rule correctly to your field number 1 over here, in order to go this way, you use right hand grip rule, where you align the index finger and your thumb, will actually tells you where the current is going. So if you do it right, you will actually see that your thumb is now pointing into the paper. So therefore you would have a current that's going in. Yeah. Let's see. So you can see that That is 1. So therefore X, the field of X has to come from a straight wire. So C and D is out. Then after that you look at your field Y. Field Y, you can see that there are actually two circular stuff. What it means is that I have one wire here and I have one wire here. And if you apply your right hand grip rule correctly, you will find that this one is going in, this one is going out. And when the current of two straight wire are in opposite direction, you will get a repulsive force, and this repulsive force will result in a magnetic field pattern that is like what you see here in Y. So for Y, it's actually caused by two straight wires, so therefore it is not a circular coil. And if you look at Z is actually a magnetic field line when you have coils of wire that goes like this. So you have a coil of wire like that. If you apply your right hand grip rule, you will have north here and south here. So actually for your magnetic field pattern, Z is actually caused by a solenoid. Okay, so Z would be caused by a solenoid. How come this is like that? Oh, I know why. So for this circular pattern, it actually is like that. So therefore this part here, the current is going out, and then this one is the current going in. So yeah, it's correct. I'm so sorry. So they are actually doing this, a circular coil, a circular coil, and what happened is that they are analyzing it like that. So they cut the coil so that this part of the coil, yeah, so that this part of the coil goes like that, you know, like this. Can visualize, and as a result you will get a field line that is like that. So it will be like this. Can visualize. I hope you, that's why I say it's better for you to come and see me, then I can orientate you. Okay, so this is your pattern Y.